Hello and welcome to this video about eigenvector proofs. In this video we'll prove this theorem involving eigenvalues and eigenvectors. I'll just step through the statement of the theorem slowly. Firstly, there's a linear transformation L that maps elements from a vector space called V back to this same vector space. And the dimension of this vector space is n, so this space is represented by vectors with n elements. And these are the eigenvalues of L, since L is equivalent to a matrix, so L can be said to have eigenvalues and eigenvectors too. And all of these eigenvalues must be different to each other and real. No complex eigenvalues are allowed. These vectors are the eigenvectors of L, and they correspond to the eigenvalues of L, like f2 and lambda2 go together as a pair. So this theorem says that this set of vectors that are eigenvectors of L must be linearly independent. So now to prove this theorem, we'll do it by induction. You should be familiar with this by now. We'll prove it true for the case where n is equal to 1. So in this case, the set of eigenvectors will contain only one vector. And when n is equal to 1, the fact that this vector is non-zero is enough to show that this set is linearly independent. So we've proven it true for n is equal to 1. The next case is n is equal to 2. The textbook decided that the case for n is equal to 1 didn't quite have enough bite in it to get an induction from it, so we'd have to go to the next case so as to be able to perform an induction. We'll create an equation as follows. If the set f is linearly independent, then these constants c1 and c2 will be forced to be 0, so that's what we're required to show. We'll use a pass theorem to write this equation. We can then substitute this equation in for 0 to get this expression. We can then use linearity to split up the function L like this. And then we can substitute the eigenvalues in for the linear transformation L, because they're eigenvalues of L and have this property. We can perform this multiplication and subtraction on these two equations to get this equation. Then we can expand the brackets. These two terms eliminate each other. Then we can factorize this expression like this to get these two eigenvalues into the same pair of brackets. So I'll just scroll everything up the screen like this, leaving some of the recent calculations there. We can say that this quantity is non-zero since these two eigenvalues are different. And then we can use the property of multiplication by 0 to get c2 being equal to 0. We can then make this substitution to get this equation. This quantity is 0 and so it cancels. And then we can solve for c2 being equal to 0. And because both c1 and c2 are 0, then by equation 1 we can say that the set f is linearly independent. So now we've proven it true for n is equal to 2. So now we have to show it true for n, assuming it true for n minus 1. This is the main inductive step. So we'll assume that this set is linearly independent. We have to find constants c1 to cn so that this equation is true. If this theorem is true for n, then all these constants must equal 0. So that's what we're required to prove. We'll start off with this equation that we've gotten from a past theorem. We can then substitute this amount in for 0 like this. We can then use the linearity of L to break up this expression into the sum of lots of L's like this. We can then substitute these eigenvalues in for L like this because it's the definition of eigenvalues. We can then multiply this equation by this eigenvalue to get this equation. I'll just scroll the screen up to make some more room. We'll subtract one of these equations from the other to get this equation. This term is obviously equal to 0. We can then eliminate it from the equation and then label this equation. We can then use the linear independence of these vectors to set their coefficients to all be 0. So now I'll scroll everything up the screen again. We can say that all of these expressions are non-zero because all of these eigenvalues are different to each other. We can use these two equations to get all of the values of c being equal to 0. This almost completes the proof, although we still have to show that Cn is 0. We can substitute all of these values of c back into the equation we had at the beginning of this main induction step to get this equation. All of these vectors are 0, so we can eliminate them immediately, leaving us with this simple equation. And then finally we can get that this last constant Cn is 0. So all of the constants C1 to Cn are 0. And because of this, we've shown that this set of vectors is linearly independent. And then finally we can do the last step, which is to say that it's true for n is equal to 2, so it's true for n is equal to 2 plus 1 is equal to 3, and so on. So it's true for all n is greater than or equal to 1, and that's it, we've proven this theorem. So I hope that you found this video to be helpful and educational. Please click like and subscribe if you did. Feel free to post up anything helpful in the comments and to share this video. And thanks a lot for watching.